Hello, in this video, I'm going to show you how to store a set of disjoint sets in a union-find data structures using Java. So in order to begin, I'm gonna first show you a quick example of how to store a set of disjoint sets like the one that you see here, and then I'm going to get into the code and explain more details about the class disjoint set, which you see here, and its variables and instance fields and constructors and toString methods and other methods that it has, which are basically find and union operation. So imagine you have a set of disjoint sets like this. You have 6 elements. A and B are in one set. C is in a disjoint set separately. And D, E, and F are all in one set, right? So imagine you want to store this. How do you do this? How do you store it? I have created a class called DisjointSet, which is going to store this set of 6 elements, or this set of 3 disjoint sets in a methodical way. I first create an array. I call this array of elements. And I'm going to store all these elements: A, B, C, D, E, and F, right? The index of A is 0, B is 1, C is 2, D is 3, E is 4, F is 5. And also I create a dictionary, or I should say hash map, that refers every element to its index, or maps every element to its index. In other words, the map that I create, and I call it the index map, maps A to 0, B to 1, C to 2, D to 3, all the way to F, which is 5, right? I put the E as well. E is mapped to 4, right? What else do I keep? I keep the size in a instance field. The size is 6. And also I keep another array called parent array, which holds a very important information. The parent array has size 6, so 0, 1, 2, 3, 4, 5 are the indices. And this parent array, parents, I should call it, holds a critical information, a critical piece of information. Basically, in this parent array, I keep the information of a forest. What is a forest? Forest is a set of trees. Each of these disjoint sets, here I have 3 disjoint sets: A and B, C and D and E and F, right? So A and B are in one set, C is in a separate set, and D and F are in the third set. Each of these sets, each of these 3 disjoint sets will need to be stored in their own trees. Let me show you how they look like. Basically, I have A and B are in one set, so A and B will create a tree like this. A becomes the parent of B. Then I have C as a singleton set, so it sees its own root and it has no children. And then I have D, E, and F. D becomes the root of its tree. E and F are going to be basically their are going to be these children. So this is the current situation. How do you store this we call this a forest, or you could call it a set of trees. How do we store these in an array like parent? Basically, the parent array is going to keep track of the parents. So who's the parent of B? It's A. What's the index of A? It's 0. So I will keep 0 here. It's an int array. Why did I keep 0 in the index 1? Because index 1 is for element B, and B's parent is A. So B or index 1 should contain 0, which represents A. So that means parent of B is A. Now, in order to show the parent of E and F, I should go to index 4 and 5, which are for the values E and F, and specify 3 in them. Why 3? Because the index of their parents is going to be 3. Parent of E and F are D, and these index is 3. For the remaining parts, 0, 2, and 3, we have no parent. A has no parent, C has no parent, D has no parent. So this parents array should keep another type of information for the roots of these trees, right? What information is critical? What I want to store for every tree is the size of the tree. So I want to keep the size of the first tree, A and B, which is 2, within this array of parents, right? So let me use a different color. Let's say a blue color. Maybe blue color is not good. Maybe the yellow color, and write down 2 here, right? Because I keep the size of the first tree in the index of its root, right? The other tree, which is only made of a root C, has a size 1, so I'm going to store 1 here. And for the other tree, the size of the tree is going to be 3, and therefore I'm going to store 3 here in its root index, which is going to be 3, because D's root is at index 3. Right? But if I store the size in the same array as the same array that stores the parent, then it's going to create a confusion, because you have both sizes of the trees and also the parent of each node in the same array of parents, right? In order to distinguish the size from the parent, or in order to distinguish which number represents size and which number represents the index, what I'm going to do is to negate the size information. So instead of 2, I put -2. Instead of 1, I put -1. Instead of 3, I put -3. So whenever you see a negative number in the parent array, that means this is the size of the tree, and the element that has a negative value in it is basically corresponding to the root of a tree, right? The root of a tree, which represents a disjoint set. The roots are also called representatives. So in this case, A is the representative of the first set, C is the representative of the second set, D is the representative of the third set, right? Now, that's why you see I have these instance fields: the parent, the element, the size, and the index, right? So I just told you all the details about the class DisjointSet. The next thing I want to show you is basically 2 operations that we define on this DisjointSet. One is called union, one is called find. Let me first tell you what find has to do. Find basically returns the representative of the set that an element belongs to. For example, find A and find B should return A, because A is the so basically find A and find B should return A, because A is the representative of the first set. Find C should return C, and find D, find E, and find F, they all should return D because D is the representative of the set containing D and F, right? So that's what find do, right? It returns the representative of the set, right? Union, on the other hand, is going to merge or combine two sets. For example, if I say, let's merge B and E, or let's union B and E, we're gonna combine the set containing B and the set containing E. So we're gonna have only two disjoint set after the union of B and E operation. That's gonna be the first set, A, B, D, and F, and then the second set is gonna be C. Why? Because, you know, union B and E will cause the set of size 2 and 3 to be combined into one set of size 5, right? When you do this, the elements array won't change. We will have the same element array. So this element array will not be modified by a union operation. The index array in the index map, this one will not change as well. The size won't change. We still have 6 elements. What will change is the parent. The parent array will have a different sequence of values. Because I'm combining, or I should say, I union B and E, I should merge these two, right? So I will say A should become D's child, right? Let me use a real, yeah. So A should become D's child. Why? Because A was the representative of the first of the set containing B. D is a representative of the set containing E. So when B and E are combined or merged, A and D, which are the representative of the two sets, should be in the same set. How do we make that happen? We make A the child of D. You may say, why didn't you do the opposite? Why didn't you put D as a child of A? The reason is because A has less children, or less, I should say, less elements in it. The set containing A has only 2 elements, and the set containing D has only 3 elements. So we use a heuristic by size and combine the two sets by merging the smaller set with fewer elements to the bigger set with more elements. So A becomes the child of D, and that means what? That means what I'm going to do is I'm going to say this -2 should now be set to 3 because A is not the root anymore. A is a child of D, and D is at index 3. And also in the index 3, which we hold the information about the set containing D with root D, we are going to add the previous value of index 0 with index 3, which means we add -2 and -3 to create -5. Why do we have to put -5 at index 3? Because now D is the root of a tree that has 5 elements. Therefore, you know, the total count of elements in D should be increased, right? That's pretty much it. That's all this union operation should do. This is my example, right? So now you basically know what are the union and find operation. Next, I'm going to show you the actual code for the union find, the constructor for this joint set, and also the actual to-a-string method which I have created for this joint set, which basically represents the set in a user-friendly fashion. It just prints, just represents the set using a with a string specifying the disjoint set. And after that, I'm going to show you an application of this class, right? Okay. So let me clear all the drawings. Let me briefly cover the constructors first. I have two constructors. One of them gets a capacity integer. One of them is a default constructor with no input parameter. The one with an integer capacity is going to initialize the hash map index by setting it equal to a new empty hash map, and then the parent array would be a new integer array of size capacity. The element would be a new element, a new array of object with size capacity. The size is 0 because originally we have nothing in the disjoint set. And then in a for loop, we're going to initialize all the parent indices to -1. The reason is when you bring a new element into the disjoint set, and the element is going to be a set by itself, the element is going to be the roots, and it's going to have no parents. So because the element is going to be within a singleton set with only one element, the value in the parent should be -1. Negative means that element is the root. 1 means the size of the set containing that element is 1, right? So that's a default value which we're gonna do for the parent array for all of its elements. Then I have another default constructor which calls the first constructor with the number 100. So we're going to assume the default capacity is 100. You could have set it to a higher value, but I just kept it simple, right? The find and union operations are as follows. The find basically checks the index map and tries to get the index for an element t, right? By the way, this disjoint set uses a generic type t for the type of values it stores, right? So for example, A, B, C, D, and F can be any type. They can be integers, they can be double, it can be a string, they can be any other class. So it's pretty I should say flexible, right? The only problem or the only restriction on T is that T should be hashable because we create a hash map on T. So T should be hashable. That means you should have a hash code and equals method for it. Anyway, so the find operation is going to get the index of T, and if T doesn't exist in the index key set, it will return -1 because we use getter default with T and -1 as a default value. If I, which is the return value of getter default, is -1, that means we haven't seen the element T before in any of the previous find operations. So let's add it to the end of the elements array, right? Element size ++ is equal to T, increase the size, and store the new index of element T in the index map. And then you return T because if T is seen for the first time, it's going to be placed into its unique to its own singleton set, and we're going to return T. T becomes its own representative, and T will be a tree of size 1 with only one root, and that root is going to be the representative of the set containing T. Then if I doesn't return -1, that means we have seen T before, so there will be an index for T in the array elements. So because T already exists in the array elements, it already exists in the parent array as well. So by using parent I, we can find out who the parent of the T is. If the T is not does not have any parent, then the parent of I would be negative, and we're gonna end this while loop early. Otherwise, we're gonna look for the parent, and we're gonna set the parent of T equal to I, so that I becomes the index of the parent of T. And we do this multiple times. Basically, by doing this, we're gonna go up from one node to the higher levels until we reach to the root. After we reach to the roots, then the parent of I would be negative. We're gonna get out of this while loop, and we're gonna return the elements at index I, which is basically the elements of type T corresponding to the index I. So this is how the find operation works. The complexity of this operation is equal to the length of the height of the tree that contains T, and using some techniques like path compression techniques, we can keep the height low. Even if you don't use path compression, the height is not going to go very, it's not going to become a very long height because of the nature of the union find operations. On the average case, on the worst case scenario, it can be very, very tall. But if you use path compression techniques, you can keep the height always very small, right? You can keep it very short, I should say. And the final operation would be extremely fast. Then you have the union operation. The union operation between the two elements U and V will work in the following way. First, we're going to get find U's representative and find V's representative. I should say we find the representative of the set where U and V belong to by calling the find on both U and V. And then we're going to get the index of that representative using the index map or dictionary. We say index.get find U, index.get find V. Now, I and J are the indices of the representative of the sets where U and V belong to respectively. I represents U's set and J represents V's set. We got a union I and J, right? If I is equal to J, that means U and V are already in the same set. So don't do anything in the union, just return, right? Otherwise, if I is not equal to J, we're going to merge the I and J. So what should we do? We need to find out which set is bigger first. Because if you remember, I told you the bigger set will absorb the smaller set, right? Or the smaller set becomes part of the bigger set. So if just also remember that the parent I and parent J are going to be negative because I and J are the representatives. So the parent information will have negative values, right? Remember that. So if parent I is less than parent J, that means parent I is less negative or is more negative than parent J. That means the size of the set containing I is bigger. So because size of set I is bigger, that means U is in a bigger disjoint set compared to V. So we are going to add V to the set of U. That means parent of J should be equal to I. So that means the root of the tree where you store V should become the child of the root of the tree where we store U. So parent of J is going to be equal to I, and parent of I will be plus equal with parent of J, so that we can update the size of the set containing U, because the set containing U now becomes bigger. Then we're going to do the opposite check if parent of I is not less than J. So that means U is in a disjoint set that has either the same size as V's disjoint set or it is smaller. In that case, parent of J should be added, parent of I should be equal to J. That means the set containing U now becomes a smaller, becomes a part of the set containing V, and parent of J should hold the more negative value because the size will be equal to the current size plus the size of U set. So parent J plus equal parent I, and then parent I is equal to J. So the opposite situation as the first one. And that's pretty much it. That's the union operation. The two-string operation, the final method that I'm going to explain here is very simple. It basically creates a map of T to set of T. That's a hash map. And then for every index key set, which is going to be every element that we store in this disjoint set, we first find the representative of that disjoint set, and then we try to retrieve the disjoint set from the map of disjoint set map. If it exists already, then we call it a set and we're going to add T to it. If it doesn't exist, that means we have seen this for the very first time, then the default value of this method is going to be a new hash set, and that set will be added by T, and eventually we're going to say map of disjoint set put rep and set. This is going to basically create a mapping between all the representatives and sets of elements stored in each disjoint set. And then at the end, we're going to grab the values and we're going to print them out. We're going to like convert those values into a string representation, and we're going to return that. So that's how the two-string method looks like. Now, let me show you an example of how to apply this disjoint set class to solve a problem. The problem I have is a very interesting one. Is called basically the synonym finder problem. You need to write a Java program that gets some input file like sins.csv. It's a file like this. This file basically stores different English words, synonyms. For example, focus and concentrate are synonyms. Study and probe are synonyms. Research and inquiries are synonyms. Concentrate and fixate are synonyms. Examination and investigation. Study, research, focus, aim, probe, investigation. And basically this program is going to scan that file. And the program should then specify whether two input words are synonyms. After the program receives that input file, then the user can basically say, are study and fixate synonyms? And the answer should be no, they're not synonyms. Or for example, are focus and fixate are synonyms? The answer should be yes, right? In order to handle this problem, I have to first read the whole input file. This is how I read it. And when I read it, I should store the information of every row using a union operation applied on a disjoint set which is originally empty. I have accredited disjoint end, which is a disjoint set which is empty. It's called sins. That means they're synonyms, and it's a disjoint set of strings because I'm gonna basically keep the relationship between different strings between like words, right? The relationship is called the synonym relationship. And basically, I will say sin that union word 0 and word 1, where you have words equal to row that is split comma, where row is going to be one line of that file that I showed you. For example, in the first line, we get focus and concentrate, and we're going to call the union on focus and concentrate. And basically, this choice is going to do its job properly, and it's going to, you know, combine the two the sets of the two words into one set, right? It's going to union the set containing word 0 and word 1. And we're going to do this for all the rows of the file. Then we're going to print out the disjoint set just for you to see that the two-string method works. And also, I'm just going to create a scanner after that, so that we can communicate with the user via keyboard. And then we're going to ask the user to enter two words to see if they're synonyms or not, and enter quit if you want to end the program. Then we're going to get the line using next line from keyboard, If the line is equal to quit, we're gonna end this while loop and that's it. Otherwise, we're gonna split the line with a space. For example, if the user say, for example, study and probe, study space probe, we should say they're synonyms. But if the user said the study space focus, we should say not synonyms, right? So if the sins.find, here we use the find operation. Word 0, the first word, is equal ignore case sin.find the second word. I don't need to say equal ignore case, that's not necessary. I can simply say equals. Then print out synonyms, otherwise print out not synonyms. So I'm going to run this so you can see how this will look like after I run it. So immediately after I run it, it should print out this map of synonyms. It says a study, inquiry, examination, investigation, and research and probe are synonyms. Fixate, aim, focus, and concentrate are synonyms. How is it possible that it has concluded all of these information with this small file? Because let's say focus and concentrate are synonyms, right? And concentrate and fixate are synonyms. So focus, concentrate, and fixate become synonyms because of the transitivity of the synonym relationship. Also, focus and aim are synonyms. So aim becomes the synonym of fixate, concentrate as well. So that's why we have these 4 elements in one set, right? The rest are going to be all in another set. Study and probe. Probe is the synonym of investigation. Investigation is a synonym of examination. And examination and the, what else do we have? A study is also is a synonym of research. Research is a synonym of inquiry. Therefore, all of these, study, inquiry, examination, investigation, research, and probe, will be synonym because of the transitivity relationship that exists, or transitivity property that exists for the synonym relationship. Because of all of that, what I'm going to do is I'm going to basically write down some pairs of words to check whether this data set or data structure, DisjointSet sins, does a correct job on the find operation. Because if the find operation doesn't work properly, the next step will fail. For example, if I say, check the relation between aim and study. If it says they're synonyms, it's the find is not working properly. But if it's a non-synonym, it works properly. So let's do some checks. For example, I will say study and aim. It says they're not synonyms. If I say study and focus, it says they're not synonym. But if I say study and inquiry, it should say they're synonyms. If I say research and examination, it says they're synonym, but research and focus says they're not synonyms. So that's how it works. As you see, the find operation also works properly. So that's the end of this demo for the DisjointSet and the end of this video. Thank you.